All right, now, rice tables, rice charts. You could call them either. And if you like look in your book or look online, you might see them listed as ice tables. They like leave the reaction part off. I like the reaction part because it really finishes off, makes everything stay nice and organized. And this is a key to being successful with equilibrium problems. Of course, the first row of the table is the balance reaction. The second row represents the initial concentration values given to you in the problem. The C is the change in concentration, and then E, the bottom row, is going to be for the equilibrium concentrations. This is a very good method of how to organize the stuff from the problems so that you don't get confused. And it's easily capable of getting confused with equilibrium problems. Okay, so we're going to start with this one right here. Now, before we actually get into the equilibrium part of this problem, I want to talk about the reaction. We have an aqueous solution reaction occurring here, and we're going to be using this to demonstrate all of the first, couple of types of problems. So we have iron 3, the ion iron 3 up here because it's a +3. We have thiocyanate, and that's not one that you had to memorize in honors or anything, but you should be able to look at that and go, yeah, that's a polyatomic ion because it's got multiple different elements and it has a charge, right? Over here to the right, though, is a new chemical species you probably have never seen or even really thought of. They're called complex ions. And it's like ferric something, thiocyanate, blah, blah, blah. We're not going to name them or anything. In a lot of the aqueous solution problems, they could give you a complex ion type reaction like this. It's nothing to worry about or be threatened by because really it just works like regular ion rules. If you look at the charge on the iron, which is +3, you look at the charge on the thiocyanate, and you can see the charges added up over here. Now this is a 1-to-1-to-1 molar relationship, one of each. Basically sort of a synthesis where the two things come together and make the one thing. But really, if you have +3 coming from the iron, you have a -1 coming from the thiocyanate, that's where they get the FeSN2+ from. Okay? And then you just treat it like regular chemical species with its molar relationships in the balanced reaction. So are we good with that to begin with? What these kind of reactions look like? And you'll see them. They're going to be in free response questions and other things where they might have a complex ion in there. But just, follow the regular normal rules that you're used to. Now let's look here at our question, our trial 1 here. We're starting off with 6 molar of our iron 3, 10 molar of our thiocyanate. These are initial concentrations. And then it says at equilibrium, we have our concentration of our product, our complex ion. This gave us lots of information to work with here, and it wants us to calculate the value of the equilibrium constant. The equilibrium constant K, that's what we're looking for here. So we're going to start by setting up our rice table. So go ahead, start setting up the rice table. Give you like a minute to do that. Initially, what do we have for our iron 3? What's the value they tell us in the problem that we need to put initially there? 6 molar, good. Okay. Now I'm going to leave off the 0.00s right now because those are part of the significant figures at the end, but it's just going to be faster. Just remember that you need to refer to the problem to figure out your sig figs at the end. All right, how much initially do we have for thiocyanate? The SCN. 10 molar, good. Now, doesn't tell us anything about the product, so we definitely make the assumption that it's going to be 0 for the product there, okay? Now, looking at this, it should be pretty obvious to you, but you should always take a moment and pause here. Which way is this reaction proceeding to reach equilibrium? Towards the products, because the products are 0. Very good, exactly right. So we know it's going towards the products. Like so. We're going towards the products. That's important to know which direction we're proceeding. Now, what was the other piece of information they told us that we can put on our table? Told us that 4 molar for what? The 4 molar is for?
Concentration. For
At equilibrium for our complex ion. So I'm going to put that right here. All right? Got that. Now, let's think about the change. Go back to the molar relationship. We have 1, 1 to 1. Now, when this reaction proceeds towards the product, you're going to lose a certain amount out of the reactants, right? So we're going to call that value X that we're going to lose out of our reactant. Now, since it's 1 to 1 to 1, the amount that you're losing of the iron should be the same amount that you're losing of the thiocyanate. Because it's 1 to 1, they're equal in the amounts that they're going to both give to the product. Does that make sense? So this is also minus X. But that also means since the two of those come together to make the one product, what you're losing out of the reactants is going to be the same amount that you're gaining in the products. Okay, so we're going to use X's. So whatever amount we're losing out of the iron, we're losing that same amount out of the thiocyanate, but that's exactly the same amount we're gaining of our complex ion. Does that make sense? And we don't know what that amount is yet, but we're going to figure it out. Or actually, some of you might have already figured it out, but that's okay. Yes, go ahead. Yes? Yes, that would be correct, except for the way I would put it in my chart up here. If this was 2, for instance, if this was a 2 here instead of a 1, this would be minus 2x instead of minus x. You see what I'm saying? Okay? But yes, you would double it in that case. So yes, it would be 8 molar if it was 2x. Because that's the change, if you didn't already figure it out. How do you figure out the change here? What do we look at? The products tells us the change in this case, because if we're starting at 0 and we're going over here to 4, guess what x is? 4. Right? Does that make sense? So 6 minus x, which happens to be a 4 here, that means this is going to be 2 molar. 10 minus 4 here, that means this is going to be 6 molar. Everybody following me so far? Now we have all of the equilibrium concentrations. 2 molar, 6 molar, and 4 molar. All we have to do is set up our expression and plug them in. We can find K now. So let's write our K expression. In this case, it'd be like Kc because these are all concentrations, or you could write it as KeQ, or just K is fine as well. Product, concentration of our complex ion over reactants. So concentration of the iron 3 times the concentration of the thiocyanate. All right, now we can plug in our values. So K equals 4 over 2 times 6. What do we get for our K?
Oh, shoot. 1/3, 1/3.
Okay, so we're not going to write it as 1/3, though. We're going to just write it as a decimal, because all K's are usually expressed in decimal numbers. So, yes. Now this is where we go back to our problem and look at everything is in 3 significant figures, right? So we're going to make it 0.333. Okay? Good to go with that? So far, so good. That's one type of problem they could give you. where you have to find K. This is the type of problem where you find K. Sound good? All right. Now, built into the PowerPoint also are the steps, so you can go back through it. Hold on, my board takes a minute. There you go, to realign. All right, and you can take a look, showing you the steps, or you can watch the video again if you want to. Definitely, that's a possibility. I have it set up though, so to line up, show you the stuff. And we end up here with our K value. Now we're going to look at the same situation from a different aspect, different perspective. Next problem. All right, this case, consider the reaction, same temperature as trial 1. So what does that mean about K? If temperature is the same, that means K is the same. So our K value is, I think it's already written in your problem, but I'm writing it up here. It's still the same number. All right, good. And this case, we're given the initial concentrations of our reactants. And we're trying to find the equilibrium concentration of our product. So definitely doing something different here. Let's take a look. And start setting up our rice table. So go ahead, take a moment, set up the rice table. I'll go ahead and put in, we had 10 and 8, right, for the initial concentrations. And we know K. That's the other thing we know. K is equal to 0.333. Now, obviously this is still a 1-to-1-to-1, so our change is going to be the same. And we're starting out with 0 product, so we know it's going to go to the right, to proceed to the right to make products here, so we know the direction. So this is minus X, this is minus X, this is going to be plus X. Now we have 10 minus X, 8 minus X, and X over here. So we're going to go ahead and plug these values into our equilibrium expression. Let's do that. 0.333 equals X over 10 minus X and 8 minus X. Here's where the fun comes in. How do we find X with this type of setup? Algebra. And who wants to do algebra? Actually, you would have to like distribute and move everything over to one side. You would have to FOIL the thing and make it just one of those like polynomial thingies. No, I'm not saying this right. And then you would have to do the quadratic formula. And in the textbooks, they usually show how to do it through using the quadratic formula. Does anybody here want to use the quadratic formula? Because I don't. No, okay. So instead, get out your handy dandy graphing calculator that you use for pre-calc and calc and all that, because we're going to graph it exactly right. This is going to be your Y1. This is going to be your Y2. Take a moment to graph it, stick it in there, and then get the graph up, give you like a minute to do that, and then we'll go from there, what you're gonna, use from your graph. So in order to do the, on your Y2, like in Y1, I put the 0.333 in there, and then Y2, I end up putting the, you do alpha y equals, and then you should have a menu that pops up. And then if you press the first one, which says n over d, which is numerator over denominator, you can set it up in there as a fraction, so you don't have to worry about order of operations. So everybody try, for your y2, do alpha and then y equals The alpha button is right below the second button on mine. I don't know if that's where yours is located. But then it pops up and it ends up making it so I can make it like a fraction. I can put it in there as a fraction. Okay, well, we're going to cover that, but thank you for bringing that up. There are two intersections, right? Are you getting two intersections? Yeah, you're getting two intersections, but you don't want to make it too complicated here. So for those that aren't as math savvy as others, we're going to go step by step here. What you want to do once you get your graph, this is what you do. Steps here. Okay, once you get your graph up, this is what you want to do. You want to hit the second button and then trace, which is really doing calc. Second trace. Then you look on your list and find intersect. On my list, it happens to be number 5. So I don't know what it is. Some lists are different, but look for the word intersect and select that number that goes with intersect. Then it's going to say first curve. And you just enter through that. Then it's going to say second curve. And you press enter through that. Then it's going to say guess. And then you press enter. This is how I do it, and this is the fastest, easiest way. So when you do the guess, it pops up, and you get x equals like 4.9986, which is really going to be 5, by the way, in terms of numbers. Now, and I don't even know how to find the second one, by the way, so just to let you know, I know some of you are really math savvy, and you're saying the other intersection is at 16, is that correct? Okay, so they're saying the other intersection is at 16. That's also an intersection. Yes. Well, this is just the change so far. We will get to the units in just a second. Now, we have 5, and we have 16 as possible values for x. And you have to decide which one is the correct value for our change. This is our change value, our x value here. Can anybody come up with a reason why 16 is not going to work here? Yes, looking here, this is going to be 10 minus 16, which gives us negative 6. Guess what you can't have ever? You can never have a negative concentration. Just like you can never have a negative distance. A distance is a measured value that is positive. That's why absolute value is always positive, because it's a distance. Same thing with concentration. You can't have minus particles in a given space, right? So that makes no sense. So this isn't the one you would want to use. You only want to use the intersection, and usually it's only 2, is the one that gives you positive concentration values. So in this case, that's why we would use this, and we would use our 5. It's usually the smaller one, yes. And it's usually the one that pops up when you do this part, the guess part. Let it guess for you. Don't sit there and scroll around and try to find it. Just let it guess for you. Or that's how Miss Shanahan showed me how to do it, by the way. So I'm sticking with her rules. Okay? So that's what we're going with. So the change is 5. And guess what? We're looking for our product here. Okay, looking for that product here. And that happens to be x, so our product concentration is 5 molar. So our product concentration is 5 molar, and that was what we were initially trying to find. So everybody good here? Because these problems, a lot of them involve using either the quadratic formula or using the graphing method. Okay. Sure. All right, let's look at the next one. So you go ahead and take a moment. Can move on to the next trial. 5 molar. All right. Trial 3. Go ahead and take a moment to set it up. Different initial concentrations. So the 6 molar, 0, we're going to proceed towards the products because this is 0 to start with. That means minus x, plus x. And at equilibrium, 6 minus x, and x. Then you just plug it in here like before. So it's going to be x over 6 minus x, 6 minus x. This one involves, the faster method is using graphing rather than trying to solve this through the quadratic method. So go ahead and take a moment to graph it. And look for the intersection, the smaller one that makes sense. Yeah, everybody's had time to graph it. You should have gotten 3 basically, because it rounds up to 3.00. So x equals 3. That means the concentration of our product here also ends up being 3. So that's great. Everybody's getting the hang of doing the graphing, right?
No, because what about
Oh, wait, no, I know what I'm doing. I forgot that.
Okay. We're having some graphing discussion in here, and they're forgetting their parentheses. Like I said, order of operations. You got to make sure you put the parentheses in the right spot, or it's going to give you the wrong number. Definitely important, order of operations. Don't forget the calculator sometimes messes that up if you don't parentheses them right. Okay. So those are the basics here. Now we're going to add on a few more wrinkles as we go. These aren't really in the notes, but these are the basic steps, and most of them are pretty common sense. You could write down the ones that you might need to remember, but like, of course, the reaction has to be balanced. Okay, that's kind of a duh. Yeah, you need the mole relationship. It has to be balanced. You want to write out the equilibrium expression for each one because you want to make sure that you're raising it to the correct power and all that stuff. In your rice table. Yeah, we're going to get to that. In the rice table, you're going to list out your initial concentrations. Now, so far, the last couple we've done, we've always had one of them with initial concentration of 0. So we knew the direction as to which it was going to go to get to equilibrium. That was a no-brainer. However, what if all chemical species had initial concentrations? Well, then we would have to do step 4 here. If we had ones that were all non-zero, we have to calculate Q. And then we would determine which way it's going to proceed. So that's important here. And we're going to do an example next that involves calculating Q. Define the change. You're going to do that based off of the molarity. The molarity, the mole relationship in the balanced reaction, like 2x, 1x, 3x, whatever, although we don't really do 1x. It's just going to be x there, based on the moles in the balanced reaction. And then we apply those changes to our initial concentrations. We subtract them out or add them based on if it's losing or gaining. And then you substitute the equilibrium concentrations into the expression, which is what we've been doing. And we solve for our unknown, or we solve for K. Depends on what type of question it is. This is also a key thing you can do at the end to check. You can calculate, put all your concentrations in there and make sure you're getting the right K value. If you're not getting the K value, you know one of them's off. So you can check your answer there. And oh, by the way, for the graphing method, I do want to point out that 2 years ago on the AP exam, one of the free responses involved either using the quadratic or graphing it. So you want to make sure you know how to do this. It did show up 2 years ago in the free response section. All right. So pointing out here, determine which way it will shift. It's either common sense because one of them is 0 and you know which way it's going to go, or you have to do the Q calculation. So make sure that you don't forget to do that. Make a rice table, rice chart, and solve. So here, this particular instance, this is the one, exercise 8, where we're going to have the difference here. We have 9 molar, 5 molar, and 1 molar. Well, guess what? We have concentrations for all the chemical species here. So what does that mean we have to do? We have to calculate Q. That's exactly right. So set up your table and let's calculate our Q. All right, so Q, what did we get for Q? Let's plug and chug, let's get Q. Basically 9 times 5, what do we get? Yes, there we go. And guess what? K is greater than Q, because we know K is 0.333. and Q is that value. So which direction does this reaction proceed? Follow the arrow towards the products. So we know the direction very good. Can't just assume it, we have to calculate Q. We are going to do one later where it goes the other direction. All right, so still the change 1 to 1 to 1. So minus x plus x. Now, just to hypothetically, had K been less than Q, those would be reversed. You would have minus x in the products, and you would have plus x in the reactants if K had been less than Q. Good to go with that? All right, so now we just have to do the rest of the solving. So we have 9 minus x, 5 minus x, 1 plus x. Stick it in the expression. 0.333 equals 1 plus x over 9 minus x and 5 minus x, like so. Stick it in there, do the graphing, find the correct intersect point. So I'll give you a moment to practice. We do a lot of the practice here to get that graphing down. What's our x value?
3.
Yeah, x is 3. Very good. X equals 3. So 9 minus 3 gives us 6 for this one. 5 minus 3 gives us 2 for this one. And 1 plus 3 gives us 4 for this one. So those are our equilibrium concentrations for all of the species. Make sense? Yes? Yes, thank you. Like the yes, there you go. Here is our answers. Exercise 8. Woohoo! Now we're going to look at a different type of problem where some of the things are going to look a little bit different. So I want you to study the problem, be able to tell me what's different about it than the ones we've already done here. Looking at the concept check. Take a moment to read it. Try to decipher what's different in this question, in this particular problem. Okay, I see some good points here. Some people have already looking here. Yes, it's gases. It involves gallons. Oh, thank you. That's one good point right there. It is, the equation is not balanced. Also, there's a volume in here. What else is it there in here that's different? The mole. We have the mole and the volume. What does that mean? We have to do one extra step here. What is that? You have to calculate molarity because The rice tables are all in molarity. So moles divided by liters. In this particular case, it's easy because the liters is 1. So basically whatever the mole is the molarity. However, that is not always going to be the case. Sometimes it might be out of 2 liters or 10 liters or 5 liters. So pay attention to that. They give you moles and liters. You're responsible for calculating the molarity. The molarities are what go in the rice table. All rice tables always are concentration based or they're pressure based, the partial pressure based, if we're dealing with the gases and the partial pressure measurements. They are never mole based. So do remember that. So yes, good point. We have the mole here. Mole, we have the liters that we need to pay attention to, and we have the unbalanced reaction. So that's a good point. We need to balance that reaction. Also the equilibrium, they told us 1 mole at equilibrium, so we have to calculate the concentration for that one too, in addition. Okay? So go ahead, set up your table. I'll write in, I have mine set up, so I'll write in my initials. This is 2.0 molar, and this is 1.0 molar. But you go ahead and set yours up. So make sure you've balanced it too. We need 3 hydrogens to 1 nitrogen to 2 ammonias here. All right, and we can, of course, since it's only ammonia in there, we know these are zeros. 0, 0 there for the products. So we know which way it's going because our products are both initially at 0. So it's going to go towards the products. We don't have to worry about the Q thing. The change thing is different though because we have new molar relationships. So what we're losing, the amount that we're losing out of the change amount is actually going to be double because the ammonia, it's 2 moles every time it decomposes. So it's going to be double the change. So this is going to be minus 2x because we're losing double the change. We're going to gain x because this is just 1 times the change. And we're going to gain 3x for hydrogen because it's 3 times the change. Now, can we figure out our x value? What do we use to figure out the change? Anyone? We use ammonia. We use our reactants here. Very good. This one. Because we have, it starts at 2, we subtract 2x, we end up with 1. So 2 minus 2x equals 1. What's x going to be? 1/2. Very good. Okay, like so. So we know the equilibrium concentration of this one is 1/2. And we know this one 3 times here, so this is going to be 1/2 times 3 is 1.5. All right. Now that we know our equilibrium concentrations, we can go ahead and solve for K. We do need to write out the expression first. K equals concentration of nitrogen times the concentration of the hydrogen raised to the 3rd power due to this 3 there over the concentration of the ammonia raised to the 2nd power because of the 2 there. Write out your expression. Take a moment to do that. And then last step is to just plug and chug. Put the numbers in, crank out the answer. So we have here K equals 0.5 times 1.5 raised to the 3rd power over 1 raised to the 2nd power. What is our K value? Sure, and since this one starts out as 2 sig figs, I'm going to go with just 2, so 1.7. Now let's talk to, just to make sure, getting this calculated K value. What does this tell me about the equilibrium position for this particular reaction at this temperature? Product favor, thank you. It's product favor. The equilibrium position lies on the right. Okay, so this one is product favor just slightly because it's a little bit greater than 1. And yes, equilibrium position is going to lie slightly to the right. There you go. So don't forget, like, K has meaning. It tells us something about the reaction. Sometimes we get into just cranking out the numbers and forgetting that there's an actual concept here. But the K value tells us something about where our equilibrium position is. There we go. There's the setup. You need to see it again. And I don't know how my animation's gonna work, or maybe my board's messed up. There you go. 1.7. Voila. All right, now this one I realize is not in the notes, but just going to point something out here. This next one, this one's not in the notes. And it's just very similar to what we just did. So we don't really need to do a problem exactly like the one we just did. Yes, K does not have units. That's a good point. You never put a unit for K. That's one of the only things in chemistry that's going to not have a unit, and K happens to be one of them. I think there's not, there might be one other thing, but K is the only one that comes to mind right now that doesn't have a unit. Oh, mole fraction doesn't have a unit. I know that one doesn't have a unit, but very rarely are you going to have some kind of measurement that doesn't have a unit. All right, looking at this particular concept check, the dinitrogen tetroxide, you know, between the nitrogen dioxide there, what is the main thing that's different here than from the previous problem?
10 liters.
Thank you. Yes, we see up here, if you look, we still have the moles, but in this case, the vessel's larger. This is a 10-liter vessel. So you would need to make sure you calculated the molarity here, 1/10. So this would be the molarity that you're starting with for this one. So that one does show an example where the liters are not 1. If you want to examine further on this problem, you can check it out. I set it up for you here. So the basic setup here, we know that initially we're starting with 0 nitrogen dioxide. You would subtract X, add 2X to the other side because it has the 2 here in the balance reaction. Then you would get your equilibriums that you plug into your calculator and graph it. You'd put this in the Y1, this in the Y2, do your graphing, and you would be able to calculate K. And also get, not K, get your equilibrium concentrations. That's what I meant. I know it's 0 because it tells me the only thing in there to begin with is ammonia. I'm sorry, it tells me, I know it's 0. In this case, we're talking about the dinitrogen tetroxide. I know it's 0 because it tells me in the problem, let's go back to the problem. Right here, the sample is placed in the vessel and allowed to reach equilibrium. That's the only thing in there to begin with. So that's how I know the dinitrogen tetroxide is the only thing in there, and that the nitrogen dioxide over here on the product side, that has not formed yet. There you go, yeah. Good question though. You forget these little nuances here and there. So don't forget here, you find your X value, then you need to calculate X based off of these equilibriums here. Okay? So 0.1 minus the X, 2 times the X, and you'd end up with your concentrations. And you can check that out in the PowerPoint if you want to go back and look at it. Now we're going to do a couple other problems with little bits of variation. Like practice number 1. Practice number 1 is different too. So take a moment to read practice number 1 and we're going to talk about it in just a second. Okay, what's the main thing here that we're dealing with that's different?
Pressure.
This one has pressures, and these are all gases here. Now, ATM. Once again, KP is always calculated in ATM. You don't want to calculate it in any other pressure unit. It doesn't work. It has to be an ATM. So if they give you like millimeters of mercury, you have to convert it to ATMs first before you can plug it in there. Anyhow, looking up here, we have pressures. Now, I want you to reframe your idea of what pressure means. Because you're like, oh, pressure, whatever. Pressure, in this case, we're talking partial pressures of each individual gas in the reaction. It's really telling you kind of an amount here. It's very comparable to concentration. Thinking about what does a pressure tell you? It tells you how many particles are hitting the walls of the container. Well, something with a higher pressure means there's got to be more particles hitting the walls of the container than something that is at a lower pressure. So a lower pressure substance doesn't have as many particles in there as, say, a higher pressure substance. So really, the partial pressures are basically kind of giving you an amount. Does everybody kind of get that interpretation and how to process the pressure values? Hopefully you understand. A lot of people get confused on that, but really the pressures are basically amounts measured by the particles hitting the walls of the container. So we can start this one right here where we don't have to write down the reaction because it's already here for us. So just create your rice table. Still the same rice table. That doesn't change. All right, the vessel initially has partial pressure of nitrogen monoxide equal to that of 0.526. So here we go. Here's our first initial. We write this in here. And a partial pressure of Br2 equal to bromine equal to 0.329. At equilibrium, the partial pressure of bromine is 0.203. Alrighty here. Now we go ahead and put in our changes. We know we don't have any of this, so that means it's proceeding towards the products to get there, to get to equilibrium. So we're going to lose 2x. We're going to lose x over here, and then we're going to gain 2x on our product side, based off of the molar relationship in the balanced reaction. How do we find x? How do we find our change? What do we look at? Bromine. Let's use bromine. This one. Find x here. Good. 0.329 minus 0.203 is going to give us our x value, which I believe 0.126. Correct? All right, so we insert that here for the x. And over here, we're going to do that here too. We put it in for our x and calculate. So this ends up being 252. And this ends up being 274. I believe. Check my numbers if I have them correct. That's what you got. Good. Wonderful. Now, we're still looking for what? KP. Calculate KP from this. Well, we need our KP expression, so let's do that. KP is equal to the product. In this case, we're using partial pressure notation. parentheses with our partial pressure notation and the P there, over reactant 1, so partial pressure of NO raised to the second power times the partial pressure of our bromine, like so. Set up the expression. Now you can insert your numbers and crank it out. And what do we get for KP? 4.17. That's what I'm getting here. And that's what you should be getting at home. So, you get 4.17? All right, very good. Equilibrium position lies to the right on the product side. The product side is favored here. 2 more problems. Hopefully we have time to do the last 2 that I want to that are slightly different, like this one. Take a look at this one. How is this one different? Practice number 2. Decomposing, sure. I don't know if that makes it that much different. Well, the Kelvin, of course, that's standard temperature. That's 25 degrees Celsius. So that seems pretty normal for the, doesn't really matter. It just has to be at the same temperature for the K to stay the same. Doesn't fully decompose. But what's noticeably different in the types of values that you're given here? Huh? Percentage, yes. You have a percentage here now. That makes it different.
I didn't think it was that obvious.
It is that obvious. You haven't seen a percentage in any of the other ones, right? Okay, yes, it is that obvious. That's what I was going for. Percentage here. That one makes it different. We have the moles. We have the liter here to get our molarity. And it wants KEQ and KP, so we're gonna have to think about that in later on. But we have concentration, so we're gonna start with KEQ, use concentration, then we'll find KP later. But it tells us that the HI is decomposing and 20% of it decomposes. Okay, so that's important information. Let's go ahead and set up our rice table. So take a moment to do that. So it says 2 moles, 1 liter. So this is going to be 2 molar here. That means these are starting at 0. So we're going to lose 2x from here. It's going to go to the right since these are 0 to begin with. Plus x, plus x. That's all good. Now, how do we find x? Or what can we find with that 20%? What information can we find using that?
That means 80% is still there.
That means 80% is still there, correct. So we can find the equilibrium concentration of HI, right? By that 20%. Yeah, that's what we're looking for here. Now, there's one of 2 ways. As just stated here, good idea. You could say 80% will remain. You can calculate it that way. Or you could just multiply it by the 20% and subtract it from the original value. So you could do either one, right? So we have the 2 times 0.2, which gives you 0.20, which is 20%, 0.4. This is how much is lost, or consumed, I guess is a better word, consumed. Let's put consumed, not lost. That changes over into product, or if you do the 2 times the 0.80, that tells you that 1.60 would be left at equilibrium. So you can do it either way. So 2 minus 0.4 gives you 1.6, right? So this is 1.60. Now we have this information and we can calculate x. So, yeah, 2 minus 2x equals 1.6. So what is that? What's x? 0.2. Very good. So that means these guys are 0.2s because they're both x directly. Now we set up our expression. So we have KEQ equals the concentration of hydrogen times the concentration of iodine over the concentration of HI squared. We plug this in. What is our KEQ, or technically KC here? Yes, very good. And since we have 3 significant figures, that's what I'm going to keep here too. 3 initial values here. Very good. Now, how do I figure out KP? What will I need to use in order to find KP? Anybody remember how KC and KP are related? Isn't there a relationship between KP and KC? Yeah, that equation thingy with the delta N, right? What was that equation thingy with the delta N? It was in the first set of notes, or the second set of notes, or something, but it's in one of the notes we've already done. KP equals KC RT delta N, right? That thing with the delta N in it, yeah. What's delta N again? What are we measuring there for our delta N? What's delta N? Products minus reactants. Yes. Remember, we're looking at the moles of the gas here. That's the N part is the moles of the gas. So, looking at the moles of the product minus the moles of the reactant. So, moles, there we go. But if you count, this is 1 plus 1, so that's 2 minus 2. So that happens to be 0. So, yes, what happens if you raise something to the 0 power? That's going to equal 1. So this whole part turns into 1, right? So, what is KP then? The same thing. Very good. KP also equals this number because if you have the same number of gaseous moles on each side, KP is always going to equal KC. Does everybody see that? Yes? Good to go? Alright. Yeah, okay, we have 12 minutes to do the last problem, so that's good. Now, we're going to take a moment and skip to practice number 6. The ones in between you can do if you want extra practice, but they're very similar to ones we've already done. But practice number 6 is a little different, so let's look at practice number 6. Last one, here we go, practice 6. You can do the other ones, the answers are in the PowerPoints, but this one, slight different variation, so wanted to show you it. All right, so Casey, for the reaction up here, it's best to always start with a rice table, so let's draw it out. R, the reaction is chlorine plus fluorine gives us chlorine monofluoride, I guess, ClF, 2 of them. All right. ICE, here we go. Tell us our KC and initial concentration of chlorine. Here we go. Initial concentration of fluorine. And the initial concentration of the chlorine monofluoride. What does this mean? Have to find Q. We have to find Q. So let's do a Q. But we have to write out our expression first, so let's do that. So K equals the concentration of this squared over the reactants. Products over reactants, do that first. Put that in there. Now we can substitute in our initial concentrations. We have all 3. We have to find Q. So find Q. Hey, what do we get for Q?
Large number.
It's a super large number, yes. You should get 666.125, whatever. Super large, yes. And I didn't do that on purpose, by the way. It's just the way the numbers came out. So this means, since we have 19.9, that K is less than Q. So which direction are we proceeding?
Reactant.
Yes, this one goes towards the reactants. Very good. That away, towards the reactants. So what has to happen here when we do our change? Yes, so we're gonna lose, or we're gonna consume the product, gain reactant. Consume product, minus 2x, gain reactant, opposite direction. Opposite direction for this one. And then we ultimately end up with 0.4 plus x, 0.2 plus x, 7.3 minus 2x. So we put that in our lovely calculator. So 19.9 equals product squared over reactant. Y1, Y2, let's go ahead and find X. Take a moment to graph that one and get it. So what do we get for our X when we graph this one? Anybody get X? Yes. That is the X value. All right, now all we have to do is finish it off. Stick them in here. Add these in. Right, so Cl2, concentration of Cl2 is going to be 0.4 plus 0.926. And everything up here is, well, this is 3, this one goes out 3, this one only goes out 2, so maybe I'll make that one go out 2, adding and subtracting wise. But let's go ahead and calculate. We did this one as 1.326 molar. The concentration of the fluorine, 0.2 plus this. .126 molar. And the last one, the fluorine monofluoride. And this is going to be 7.3 minus 2 times. And this one I might just do 5.45 molar. So those are the rice table problems, rice chart problems in a nutshell. Probably see different variations throughout the problem sets in the labs and free responses. We're going to do a few more and do some more practice next class, going back over other representations of equilibrium problems. And you can go ahead, with your problem set now